So our next paper is the Best Paper Award winner. Huang Chen is the speaker. She's going to bring us back to Earth. She's a researcher from Huawei Theory Lab at Hong Kong Research Center, currently working on network configuration management and its intersections with machine learning. Dr. Chen received a PhD from Hong Kong University of Science and Technology in 2020. Thanks.
Thanks for the introduction. Good afternoon. This is Huang Xun, a researcher from Huawei Theory Lab at Hong Kong Research Center. Today, I'm going to present our recent work titled Soft-Defined Network Assimilation, Bridging the Last Mile Towards Centralized Network Configuration Management with NAssim. As one of the most important infrastructures, networks support numerous applications. In a perfect world, all network devices should have homogeneous device models, which means given the same configuration command, they should execute the same actions. In this way, the network operator will be very happy. Unfortunately, the real network consists of heterogeneous device models. Because large enterprises will operate network devices from multiple vendors. And in the meanwhile, they will gradually introduce a new device model into the network, resulting coexistence of legacy and latest devices. It is a pain for the network operator to manage a multi-vendor network. And in common practice, we will have a soft-defined controller situating between the up-layer network functions and heterogeneous device models. And it's desired that the controller can present a logically centralized control plan to configure multi-vendor devices as if they are the same. Thus, the network operator will define a unified device model at the controller, and then they should understand the menus, find correct commands, and draft template and provide mapping rules to the unified device model. And then they should repeat the same process again for a new device model. This would be a very tedious and error-prone process. And this is a process of introducing heterogeneous network device into a centrally controlled existing soft-defined network. And we define this process as soft-defined network assimilation, SNA in short. The key problem here is the mismatch between two configuration models, the heterogeneous vendor device models and the unified model at the controller. And current SNA process requires significant human effort to bridge them. And we seek a more automatic and efficient manner to accelerate this process and liberate network operator from most tedious tasks. And our basic insight to tackle this problem is to design a system that can understand menus as network operators. It should first extract and validate a reliable vendor device model from its menu, and then infer the mapping between the vendor device model and the unified device model based on semantic information from menus. However, realizing this idea in practice will encounter three challenges. The first is menu format heterogeneity. There is no standardization for menus. They are organized and formatted uniquely for different vendors. This makes it hard to enable automatic menu comprehension. And the second challenge is error and ambiguity in menus. After all, menus are human-written documents. It's inevitable to have mistakes and typos. And it is also impractical to manually audit the menu page from the first page to the last. Thus, while handling this issue automatically, it's critical to extract reliable vendor device model from its menus. And the third challenge is heterogeneity between configuration models. Due to a large number of CLI commands and parameters, handcrafting this mapping is tedious and error-prone. Automating this process requires a powerful semantic comprehension model to understand and match similar network configuration contexts. Therefore, we propose NAssim. we designed Parser framework to address the first challenge, which mainly features a vendor-independent device model corpus format. And we then designed Validator to address the second challenge. We finally identified many error and ambiguity in the menus and successfully construct a reliable vendor device model from mainstream vendors' menus. And we further designed Mapper to address the third challenge. We trained semantic similar inference model for network configuration domain to generate mapping of parameters between heterogeneous configuration models. And we also released a Validator and expert query dataset of past menu corpus for future research. And this is the overview of the NAssim. In the following, let us take a closer look at three key components. And the first component is Parser. The key inside of the Parser is from investigating major attribute of multiple menus. Despite diverse style, we found that all menus should serve the same purpose, showing us how to configure the devices. Thus, they should cover all the CLI commands supported by the devices, their function descriptions, their working views, parameter and descriptions, and some representative examples. Thus, we designed a unified format with its dictionary with keys and value type constraints as shown in these figures, and to consolidate diverse menu styles. And for each mainstream vendor, we build a parser to concatenate its menu to this unified format. And here is the sample corpus generated by our parsing framework. In this way, we can extract all essential information from the menus and in the meanwhile normalize diverse menu style into a unified format to facilitate the following processing. And the second component is the validator. And the key inside here is that menus are not fully reliable. We identified two main types of error and ambiguities. The first type is syntactic ambiguities. For example, here is an example, a CLI command from vendor menus. It has an unpaired left bracket before the remote S symbol. And there are multiple potential valid fixing options, and choosing which require judgment from the experts. And the second type is hierarchy ambiguities. For example, these two views in another vendor's menus share the same example snippet. Thus, we cannot surely tell whether this MSDP command enabled the first view or the second or both. Despite all this error and ambiguity in menus, we still want to construct a reliable vendor device model from the menus. Thus, we designed a three-level validation scheme. The first part works on command level. In this part, we find out command convention in the menu preambles and express them into their equivalent backwards normal form. And thus, we can generate a CLI command syntax parser and leverage them to identify syntactic errors. And in this way, the expert can audit all incorrect ones in a more targeted and efficient manner. And the second part works on inter-command level. Here, we want to derive the CLI, the tree-based hierarchy implicitly in menus. Thus, we leverage the example snippet in the menus. Example in the menus generally present an instance of CLI command and its parent command. So we designed a graph model to infer their relationship on the CLI template level. Please refer to our paper for more algorithm detail. And for the hierarchy ambiguity, we will quantify the certainty of our derivation to facilitate the expert to audit later. And the third part work on snippet level. Here, we further leverage the configuration file collected from the running devices Thus, they have correctness guaranteed for validation. For CI instance in each configuration file, we will check whether their match CI template form correct relationship on our derived hierarchy. And we will record all the unmatched one for the expert to audit later. And here, let's have a quick look at the result of vendor device model construction phase. Our parser and validator successfully construct reliable vendor configuration models from menus of 4 mainstream vendors. And we also identify more than 200 error and ambiguity in menus. Please refer to our report for more details. And the third part of design is the mapper. By investigating the existing handcraft mapping process, we found the key of the SNA is to pair semantically similar configuration items. Since the parser and validator have obtained the vendor device model with abundant semantic information from menus, and the parameters in the unified model are also enriched with description tags assigned by the experts, we can design the mapper to understand this network configuration context by applying recent advances in natural language processing. Our result model is NetBERT. Let's see how it works. For each configuration item, we want the model to identify its semantic similar ones in the counterpart model. Thus, for each pair of them, we run the following process. First, we extract their key context information. And for the vendor device model, we found that the parameter names and its description, the CI command and its function description, and the working view are valuable information for this mapping task. And for the unified device model, we just directly retrieve its description tags assigned by the expert. And in the next step, we leverage the BERT, the most popular NLP pre-trained model, and we train a domain-adaptive version to encode the contextual information into embedding vectors. And then we will evaluate a cosine similarity between the embedding vectors to quantify the semantic similarity between the contextual informations. And we will run this process multiple times so that we can get a ranked list. And in this way, for configuration items, the mapper can recommend top K semantic similar mapping parameters. And the power of NetBERT comes from two sources. The first is a pre-trained model, SBERT. It is pre-trained on a large natural language inference data set with sentence matching objective. However, it has limited performance in a domain that is never seen in the pre-trained corpus. Thus, we introduced the second source, a domain corpus of network configuration domain. To generate it, we leverage a few mappings labeled by the experts. And these are all positive pairs. Thus, we use a random sampling to generate negative pairs and to form the whole domain data set. And then we leverage this domain data set to conduct domain adaptation fine-tuning to get the NetBERT. And now let's have a look at the mapping performance. The mapper acts as a recommender to generate most likely mappings. Thus, we adopt recall at top K for evaluation matrix. Higher recall at smaller K implies that the mapper is more helpful. We use cross-vendor tuning and validation. And as shown in this figure, the fine-tuned NetBERT outperforms all the other models. This is because we adapt the NetBERT model to the domain of network configuration. For saving the human efforts, for Huawei case, we can find correct matching within top K recommendation with 89% accuracy. Thus, in this setting, the network operator only needs to refer to the menu 11% of the time. resulting acceleration of mapping phase by around 9 times. And to conclude, we list a few key takeaways. Firstly, soft-defined network assimilation is essential for managing multi-vendor network. Our solution, NAssim, seeks to transform tedious and error-prone SNA process to automatic and efficient manner. Configuration manuals as human written documents are not fully reliable, including inevitable errors and ambiguities. NAssim features a unified parsing framework, a multi-leveled validator, and a mapper using the domain adaptable model to produce mapping between heterogeneous configuration models. And we also release a dataset for future research. And currently, we are transferring this technique to Huawei Network Automation Engine to better support service to Huawei's business customers, including network carriers, data center, and large enterprise network. And thanks for all your listening. I'm happy to take any questions.
Thank you for the great talk and congratulations. My name is Sharad from Microsoft. So I'm wondering about OpenConfig and gRPC, or GNMI rather, the gRPC network management interface. So when I talk to some network operators, they tell me something like 75% of their config is covered by OpenConfig, and the remaining 25% is very specific to the particular device, and so they have to go off and do that manually. And I'm wondering if you can tell us about how that coverage looks like for your system, and in particular, the trade-off between contributing to OpenConfig and GNMI versus building a separate system to tackle that problem.
Okay. Thanks for this question. It's a very good question. Actually, it's also mentioned in our reviewers, by our reviewers. And here we mainly adopt the CLI command as the basis of our vendor device model, because in Huawei's network there are many, and Huawei's customers' network, there are many legacy devices. These devices do not support young configuration manners. So I think young-based configuration is a trend, but our work is from a very practical perspective to address the challenge faced by our product group. But I think our basic methodology, the parsing, validation, and then mapping, these methodologies can be also applied to the young-based configuration. Actually, we have added a discussion session in our paper, so that I think you can refer to our paper for more detailed discussions.
Hi, Steffen Smalka from Google. Thank you for the fantastic talk. So networks need to be very, very reliable, right? And here you're using a lot of sort of approximate methods, maybe heuristics, machine learning, and so on. I'm trying to understand a bit better how you bridge that gap. Like, might this be a tool, and then you also use some human inspection to sort of fix areas where what you come up with is only approximately correct? Or how do you deal with errors, I guess, approximations?
Yeah, thanks for this question. This is a very great question. And actually, we did not position our work as an end-to-end automatic system. Actually, it's a system framework. I think the fundamental reason is that our major source is the manuals, configuration manuals, and these are all human-written documents. Although network operator will read them, but it's not fully reliable. So that when we designed our system, we try to make it, the whole process can be understandable by our network operator. And if they want to intervene, they can. Because our corpus is in JSON format and is understandable by human experts. So it's the same for the mapping phase. We just make our mapper to act as a recommender. because NLP is the best effort technology, so we cannot guarantee that we find the correct mappings. So, but we recommend if we can make our model recommend correct mapping within the top K recommendation, then the network operator doesn't need to rehold the manuals to find out these correct mappings. So I think this is try to accelerate this process and liberate the network operator from some tedious tasks, but it cannot replace the network operators and their experience of managing multi-vendor network.
Thanks.
Okay. Thank the speaker.